going to record, and I'm just going to say briefly so that other people that see this later, even though there's no homework from section 3, 4, and 5, I will make it very clear the sorts of problems I would want you to know for the purposes of the final. They are things that we'll work on together in class for sure. We're going to finish this material like champions, okay? We're going to be in good shape in terms of when we will finish. I think we'll be done actually with material probably like at the beginning of next week even, okay? So, other questions? Any other questions? Well, we talked about vector valued functions last time. We kind of introduced the concept of vector valued functions. And I hope I made it clear that this was just an extension of the line paradigm, yes? So like when we had lines, when we were dealing with a line, we had several forms of the line. We had the vector equation of a line, yes? And the vector equation of a line, we wrote as x, y, z is equal to, okay, and there was like some point, x0, y0, z0 that I thought of as a vector. And then I added any multiple of the so-called direction vector to that, yes? And then we got from that the parametric equation, the parametric equations of a line. The way we got that was by distributing the t and then collecting the x, y, and z terms together. And we got that x had to be x0 plus at, y had to be y0 plus bt, and z had to be z0 plus ct, okay? So we parametrize a line in this way, but that came from a vector interpretation of the line, yes? Okay, we kind of saw that all together back when we were dealing with lines. And the only thing we did in section 1 was we generalized from lines to any curve, yes? Now it could just be any curve at all. And we have these vector equations. We called them R of t, which were, you know, some function of t in the first coordinate, some function of t in the second coordinate, and some function of t in the third coordinate. And instead of thinking about the vector necessarily as the output, even though it is, we thought of the tips of the vectors as the output. And those tips form a curve in three-dimensional space, okay? Might seem kind of bizarre that we would, you know, instead of thinking of the vector itself, we think of the tip of the vector, but the tip of the vector actually tells us what the output vector was, right? Because we think of that vector emanating from the origin. So we always know where the point of emanation is. It's the origin, okay? But the collection of all these triples gives us a curve in three-dimensional space that we call the space curve corresponding to this vector field. And we did some examples last time. We had that little spiral staircase, yeah? We even had that crazy example at the end where we were looking at the intersection of some kind of parabolic sheet with an ellipsoid, yeah? And we tried to parametrize that, okay? But now what we're going to talk about is, okay, let's do some calculus on these vector valued functions. That usually means we want to do differentiation and integration of some kind, all right? And the integration side of things is going to get way more sophisticated, and the differentiation part is going to get way more sophisticated when we get into Calc 3, and we'll see what, you know, what sorts of things are actually useful in the context of integrating when it comes to vector valued functions. Here's a hint, you know, a lot of it has to do with work, like the notion of work, yes, the physical notion of work, and that will involve some integration that you'll see kind of at the end of Calc 3 actually, okay, if indeed you do take Calc 3. All right, so let's dive in here. So this probably isn't going to be all that big of a surprise to you. What is the derivative of a vector valued function? Well, we have the limit definition. Doesn't this look familiar? Yeah. You remember, f prime of t was equal to the limit as sometimes we said h goes to 0, f of t plus h minus f of t all over h. Okay, we've just replaced h with delta t. We've replaced f with the actual, vector field, r, yeah? And we define the derivative the same way. And you might say to yourself, yeah, but is that helpful? Is it helpful to compute that thing? Is that telling us something about the vector field? And it turns out the answer is yes. We'll see what that is here in just a minute. But alternative notation, you could write dr dt, okay, like that with a little arrow over r to tell you that this is a vector field that we're taking the derivative of, okay? So dr dt is r prime of t, okay? So this ought not be a surprise to you that this is how you compute a derivative, okay? And actually, when we do this difference between r of t plus delta t and r of t, that difference really is you really are gonna go down to the level of coordinate functions, aren't you? In the end, you're gonna have to take that difference in the first coordinate, the second coordinate, and the third coordinate, okay? Because that's how differences of vectors work. Remember, r of t is a vector in the end, yes? So that difference is gonna happen in the coordinates, and dividing by delta t is simply scaling this vector by something, right? We're scaling it by 1 over delta t, basically, okay? So in the end, when you take the derivative this way, it just basically amounts to going into each one of the coordinates and computing the derivative separately, yeah? Any questions on that? We're gonna see some geometry here in just a minute, but any questions on that? Okay, so like I said, when you go to compute the derivative, it really goes down to just going to each one of the coordinates. And so the derivative of r basically will just be, you take the derivative of the x coordinate and the derivative of the y coordinate, okay? Or the derivative of the z coordinate if it happens to be a vector field in space, okay? So that's interesting. Here's a picture. Oh, here, first of all, a question. Is r prime of t a vector valued function or a scalar valued function? So look back over here. R was a vector valued function. Is the derivative also a vector valued function? Yes. It is once again a vector valued function, yeah? The output is a vector again, okay? So we have the vector valued function itself, and then the derivative is also a vector valued function, okay? So is r prime of t a vector valued function or a scalar valued function? It's vector valued. It's a vector valued function, okay? Here's a picture. R prime of t, and this curve right here, I'm telling you, is kind of moving in this general direction, okay? R prime of t is going to be basically like a tangent vector at a given point, okay? So if this is r of t, okay, with terminal end right there, then r prime of t is going to be a tangent vector at that given point, yeah? That kind of makes sense that that should be the case, correct? Because derivatives of one variable functions back in calculus were giving us slope of a tangent line, yes? For this, it's going to give us basically a tangent vector at a given point on the space curve representing r of t. Okay, and you can kind of see why that happens to be the case. Here's r of t, here's r of t plus delta t, right? So t plus delta t would move us along the curve a little bit. And then what's this vector right here? Well, that's the difference between r of t plus delta t and r of t. That is, this vector right here is the difference between those two vectors, yes? It kind of completes that little triangle. So if I let delta t go to 0, do you see that that vector is going to get closer and closer and closer to like being tangent to the curve? Yes. As I let delta t go to 0, these two vectors are going to get closer and closer, and that vector is going to get closer and closer to a tangent vector. You might say, yeah, but it's also getting really small. Well, what's going to stretch it back out is dividing by delta t. Yes? Like if I were to let this thing, get closer and closer and closer like this, you could see that this vector that joins these two ends is getting smaller and smaller and smaller. But if I divide by delta t, it's going to stretch it back out again. Yeah? And eventually you get this nice little tangent vector right there. That's what's going on. Okay, so in the end, the derivative is kind of measuring the rate of change in the x direction, y direction, and z direction, and that gets captured in a tangent vector to the space curve in the direction of movement along the curve. Okay? R prime of t is a vector tangent to r of t and in the direction of increasing values of t. Okay? Any questions on that? So this little picture kind of captures nicely what's going on in general. Okay, but any questions on that? So in some sense, this vector is kind of giving us a velocity for a point that's moving along this curve, right? As we kind of move along the space curve as t increases. It gives us a velocity. It gives us both a direction and a magnitude at that point, yes? So every time I say that now, I think of Vector from Despicable Me, right? Committing crimes with both direction and magnitude, yes? And that's exactly what this thing is doing. It's telling us both direction and magnitude of movement along this curve. It is a velocity vector, yeah? That is what's going on. We'll talk about that more in the next section when we start thinking about acceleration. And acceleration will literally be the second derivative of the vector valued function. Acceleration is what's going on. How am I being pulled as the point moves along on the curve? Okay, that's what the acceleration vector is doing. That will be the second derivative, but that's a discussion for another day. Okay, let's do some examples. So what I want to do is go back over to this thing over here that we were working on yesterday. Okay. So I'm going to close out this nice little picture. Okay, oops. Get rid of the orange thing here. Yeah. Okay, so this curve right here. Okay, remember this? Okay, and remember this. Like we could actually, oops, I don't need to show that. I can just play it though. Right, so there's this vector valued function right here, yes? Okay. Another thing that we might care to do is kind of graph the derivative of this thing, yes? And it's actually most helpful to see the derivative on the curve itself. Remember, the derivative is a vector, right? It's not just a number now, it's actually a vector. So first of all, in this problem, we had x equal to, what was x? X was 2 sine of t, yes? And y is -6 cosine of t, okay? So what is, let's say dx dt? What's that? Dx dt is 2 cosine of t, exactly. And dy dt is, right, 6 sine of t. Thank you, yes. Okay, so in other words, r prime of t, in this case, which is going to be, the x coordinate differentiated, the y coordinate differentiated, is 2 cosine of t, comma, 6 sine of t. Okay, so let's go ahead and capture that somehow, okay? And I just want to show you how you can do this in GeoGebra because it's kind of nice. I have to go down to the bottom here though, okay? So what you do is you go curve, okay? How many expressions do I need? 2 or 3 in this case? This thing is in 2-dimensional space, correct? I mean, it basically is in 2-dimensional space. So I'm going to say there are 2 here. Okay, oops, what in the world? Come on now. Curve, are you serious? Delete that, right? So curve, okay, I click on this. The first expression is 2 cosine of t. Cosine of t. What's the second expression? 6 sine of t. Okay, parameter value t. And what was t going between? 0 and 2 pi, I think is what it was for this thing. Yes. Okay. Now, the thing is, I don't necessarily want to graph this thing. Okay. What I want to do is I actually want to form a vector for this. So vector, okay. And I'm going to do a start point and an end point, okay? The start point, I'm going to have be, I have to figure out what this thing is. The start point is going to be R of S, okay? Oops, look at this thing. It's disobeying my, I walk away and then it messes everything up. Okay, so vector, what do I want? I want a start point and an end point. Okay, the start point is going to be the tip of that vector, okay? So the tip of that vector is R of S. Okay, the end point, I want it to be R of S plus, okay, so hang on a second here. That guy right there, so I want it to be that guy plus D of S. So R of S plus D of S. I think that should work, okay? So that's the end point. Okay, so do you see it? There it is right there. You see that thing? That's kind of cool. So I get my tangent vectors right there. Notice that it kind of shortens a little bit as it kind of makes a turn. Do you see that? This thing makes a turn, it shortens a little bit, so I don't have quite as much velocity there. Yeah. It has its most velocity as it kind of moves from the really extreme curvy ends, and it kind of moves between those two things. So the tangent vector takes on a little bit more length right there. I think that's kind of cool, right? Any questions on that? Questions? Let's work on another one. This other one that we were working on last time. So let me see. Clear that out. Okay, right. Remember, we're living in 3-dimensional space, but we're kind of watching this happen in 2-dimensional space, which is kind of fun to do. Yeah. Oops. But let's go back to 3 dimensions here. Okay. I am going to pause this thing. And let's look at this other one. Remember, it was 3 cos t, 3 sine t, 2t. So I'm going to get rid of some of these, and we'll play around with this a little bit. Okay. So 3 cos t, 3 sine t, t. Yes. Remember this? This gave us this kind of like spiral staircase thing that was going on. Yeah. Okay. We even created a vector that represented that, and we were letting this thing play, okay, go all the way around on this thing, right? So same sort of thing. I'm going to change, so here the parameter I'm using here is A actually, okay? I'm going to change this thing. So that thing was W of A, but the first thing I need to do is take some derivatives. Here I had X equal to 3 cosine T, Y equal to 3 sine T, and Z equal to 2T, right? Okay, so this was like R. Okay, this was R of T. So what's r prime of t going to be? What's the derivative of the first coordinate? Yeah, -3 sine of t. Okay, then what? 3 cosine of t. And the z, the derivative of the z coordinate is 2 all the time, yeah? So we're going to keep that in mind. We're going to create a little tangent vector down here at the bottom. Oh man, let me erase this thing. Okay. Okay, so let's go down to the bottom here. Okay, it's going to be vector. Oh wait, I need to see. Let me just make sure. So the first thing I need to do is actually create a collection of points here. So curve. Now I need 3 expressions. Okay, the first thing is -3 sine of t. Second thing is 3 cosine of t. Okay, and then 2, and it was t, and it was from 0 to, what was it, 4 pi or something? Something like that, yeah? Okay, so I had that. Okay, so that's the derivative right there, but now I want to have a vector that emanates from the actual point itself. Okay, so it was like vector. Here we have a start point and an end point. The start point I want to be the terminal end of my vector valued function, which was w of a. And then the end point, oh man, they have f. They represented this thing by f. So it's going to be w of a plus f of a. Okay. And I think I can go like that. Now you see it? You see the little tangent vector right there? That's kind of neat. Plus that one basically looks the same the entire time, doesn't it? Yeah? That one looks like it kind of has the same length the entire time, but it's just kind of spiraling up that thing. Does that make sense? So we have our little tangent vector of that 3-dimensional space curve in that case. All right. So I just wanted to give you sort of a visual illustration of what was happening there. Any questions? Any questions? All right, going back. Let's see, I'll pause this. Okay, and back in here. All right, just some terminology that the book tends to use. Differentiation of a vector valued function. If the derivatives of each component function exists on an interval, you call this vector valued function smooth. Okay, it's smooth. That just means that there's not, really what it means is there's not like any sharp, jagged edges in the actual space curve itself. Okay. In addition, you don't want the derivative to be the 0 vector anywhere. Okay. If the derivative was ever the 0 vector, that means movement has ceased at that point, right? The tangent vector tells you where you're going, essentially. And if the tangent vector is 0, that means that movement has ceased at that point, yeah? So smooth would also mean that we continue to move along the curve smoothly the entire time without stopping, yeah? We might slow down sometimes and go faster at other times, but we don't ever even want to stop. That's what smoothness means for a vector valued function. Any questions on that? Well, I already did the second example. It was the 3-dimensional one. Properties of the derivative of vector valued functions, basically all things that you would expect to be true. For instance, you can factor out constants and take the derivative. Derivatives of sums and differences are sums and difference of derivatives, yes. If you have a w of t is just a scalar function. If you have a scalar function times a vector valued function, you basically can apply the product rule, okay? It's going to be w of t times r prime of t plus w prime of t times r of t. Now, here's what's kind of weird. If you have 2 vector valued functions and you take the dot product, it turns out that you apply the product rule with the dot product in place of the actual product that you're computing, yes? So you kind of have a dot product rule, but you also have a cross product rule, okay? Those are both just facts that you can take to the bank. There's also a chain rule. See that? See the chain rule, number 6 right there? You have a chain rule. If you, instead of putting t inside of the vector valued function, you put the scalar function w of t, you basically apply the chain rule. Chain rule works, okay? And this one's kind of interesting. We can talk about this later. Yeah, we'll talk about, yeah, well, actually, I'll talk about number 7 right now. Do you guys remember if we had a vector and we dotted that vector with itself, what was that? What's that? It's the magnitude of the vector squared. That's exactly right. That's the magnitude of the vector squared. So this last property right here says that a constant is equal to the dot product of r at t with itself. Okay? But that means that that constant is equal to the magnitude of the vector r of t squared. Right? That's what that means. Which means, by the way, that the length of the vector field at any point, the length of the vector field at any point is just equal to the square root of c, which, by the way, is itself just a constant, right? So what that's saying is every vector, or every vector that we get from the vector field has the exact same length, okay? It all has the exact same length. And what that means, by the way, is that, well, what that means is the following, okay? Let me just try to draw a little picture here. This, hopefully I don't totally butcher this. In fact, I already am. Here, let me draw a picture. What it means is the following. There is a sphere, okay? There is a sphere, and the radius of that sphere is the square root of c, okay? And the space curves, let me just say, this picture I have right here, like here's the z-axis, here's the here's the y-axis in this direction, and here's the x-axis, okay? So this thing kind of goes through right here. The space curve r of t actually lives on the surface of this sphere, right? Because all of those vectors have the same length. Do you know what I'm saying? So the space curve itself actually lives on the surface of this sphere, yeah? So that's r of t right there. That's the space curve generated by the vector field r of t. Now, what that means is that if I were to compute, like, at any point, I don't care, like a particular vector r of t, and then I look at its tangent vector, okay? I look at its tangent vector at this point, maybe it goes like this. What do you think is going to be true about this vector right here and this vector right here? I'm telling you, since that vector is touching that sphere, and you know the curve is on the surface of that sphere, those two vectors are going to be perpendicular, yeah? Because the space curve actually lives on the surface of that sphere, all of the vectors r of t are going to be perpendicular to the tangent vectors. Think about that. It's because the tip is right on the surface of that sphere. So that's what this is saying right here, okay? If r of t dotted with itself is always a constant, that means that the space curve is on a sphere. And therefore, every one of the vectors in the vector valued function is perpendicular to its tangent vector, yeah? Now, that might not seem like a big deal right now, but I'm telling you it is. It will be a big deal later on. It turns out that has massive ramifications in physics, for sure, okay? Any questions on that? I mean, I know that that's kind of mysterious, but that's all that's going on there. The dot product being a constant means the vector valued function, or the vector valued function has space curve that lives on the surface of a sphere, And that forces every one of these vectors to be perpendicular to the tangent vectors. Yeah, I think that's kind of neat. Okay. Any questions on that? All right. What about integration? Well, okay. What is an integral? So like an indefinite integral, I would just like integrate each one of the coordinates. And by the way, these are not absolute values. They look kind of funny up there. Those are just supposed to be brackets. Yeah. Okay. So the integral of R of t, you just integrate each coordinate term by term. Okay. Definite integral, you just integrate each coordinate term by term. You do the same definite integral. Now, you might say to yourself, yeah, but what does that mean? You know, because we're not really talking about area anymore, are we? We're integrating like an actual vector field now, yes? There's not like an area under a curve interpretation that I have anymore. Well, believe it or not, the integral on its head is actually telling you something like an average value for the function over an interval, yeah? Do you guys remember how to compute the average of a function over an interval? You guys remember like what the average value of f is over an interval AB? Do you remember? Well, you go 1 over b minus a, and then you the numerator is actually the integral from a to b, f of x dx. Yeah? Remember that little formula? What this is telling you is that integration is basically giving you a scaled average value for the function on the interval. Yeah? Because after all, this formula right here is saying that the integral from a to b, f of x dx, is basically this number, b minus a, times the average of f over the interval. Okay? So I know that we said that integration was area under a curve. And then we kind of waved our hands and said, oh, yeah, it's negative sometimes when you go below the x-axis. But what was really going on is we were computing averages. Yeah? We're computing like average values for a function, or at least scaled average value. I'm telling you, that is one of the biggest tragedies in calculus instruction, that students don't really get that in their calculus instruction. Most people don't talk about that. I think that is critical, that you understand that integral on its head is really like an average. Yes? Therefore, when I integrate a vector valued function coordinate by coordinate, what am I basically finding in each coordinate? Kind of the average x coordinate, basically, yes? It's like the scaled average x coordinate and the scaled average y coordinate, etc. It would be the average if I divided each one of the coordinates by b minus a, then it would flat out be the average, yes? Averages is something that makes sense no matter what I'm talking about. 3 dimensions, 4 dimensions, 5 dimensions, doesn't matter. I'm not always going to be able to say that something has some kind of geometric area interpretation. So integral in this context, we're talking more about averages. Does that make sense? Hopefully. Okay. Here, you don't necessarily worry about C in the same way that you did when you were just dealing with one coordinate at a time. Okay. Like you could, in theory, add different constants to each one of the coordinates. Yes. Like if I did an indefinite integral, like the first thing right there, I could, whatever the answer is, I could go plus C1. And then the second one would be like plus some other constant C2. Because when I take the derivative, those constants would go away anyways, right? So you, in some sense, have a little bit more freedom, but we're not going to freak out about that too much. Okay? Any question on that? I don't want to spend a ton of time on the whole integration concept. That's something that will become much clearer at the end of Calc 3. It will be clear why integration of vector valued functions is important. But for right now, think of it as an average of some kind, or a way of turning a way of turning velocity into position or something, like trying to go backwards from velocity to position. Okay, is another way you could think about it. Any questions on that? I think that's all I had. That is all that I had right there. Okay, so we're actually done with 12.2. We'll start using this stuff next time.